And so I'd like to first of all thank the crew for inviting me for giving a talk. Uh, and A little bit about myself, as Dr. Flo already introduced myself. I would just like to add a couple of things. My master's thesis was based on probabilistic study of grid-connected wind farms, and then we started my PhD in continuation with that, which has got transmission expansion planning for the western part of the U.S. in with regards to new wind farms. The outline of the presentation is kind of simple. I'm going to go over with the definition of unscheduled flows at the bulk interconnection level or the transmission network level, the causes of unscheduled flows. These are primarily two: network interconnections and deregulation of electricity industry. These are kind of broadly the overviewing reasons. I'll go into details of that in a little bit. I'm going to provide an oversimplified example of how loop flows, how can we visualize loop flows and then model unscheduled flows from that. An accommodation technique will be discussed next. At the core of the accommodation technique, we have the simple linear estimator. Then we're going to talk about what does wind do to these unscheduled flows. Essentially, how does the nature of unscheduled flows change with wind penetration? A small example will be provided later on, that is the IEEE 14 bus system. Then we have used some practical data from wind farms to simulate and estimate unscheduled flows. Then we compare the results of estimation, provide an advanced estimation technique, and then we're now making the transition towards bulk interconnections from these experimental test setups. And then we'll have some concluding remarks. Unscheduled flows are essentially defined as deviation of power flow on transmission lines from the market perspective. The reasons, as I already mentioned, are the interconnections and deregulation of market. At any node of a transmission network, we'll have multiple paths available for the power flow. So essentially, the division of power will occur as per the circuit theory basics, as in depending on the impedances. The other reason is in electronic tags, the way electricity is traded is using something called as electronic tag, and I'll show us a very elementary electronic tag later on in the slide. Only a single path for a transaction is showed. So power has essentially multiple paths to flow, but we allocate in the market level only a single path. So this is where the inconsistency starts, and that is the main reason of unscheduled flows. And again, these paths or lines in practical bulk interconnections are operated and owned by different companies, since that's the philosophy of deregulation. Here's a very small network. I apologize for the clarity of the diagram, but it has two conventional generators, or let's just call it generation companies. The first generation company is up top here, and the other one is here. This is the bus number 1, this is bus number 3, and this is bus number 2. We're trying to supply the load at bus number 2 using the two generation companies, trying to set up the contracts for them. So what the market expectation is going to be here is, suppose generation 1, which is right here, wants to supply about 180 megawatts to the load, and the generation company 3 wants to supply about 320 megawatts to the load. So the way the electronic tag will typically be set up is, this is just an example, there might be many possibilities, but this is one of them. So the generation company 1, which is the source, uses path 1 to 2, which is right here. It is expected to flow on path 1 to the load with I don't need it to the load, and the power flow expected is about 180 megawatts, whereas the generation company 3 is supposed to supply about 320 megawatts from down here to the load, which is about 320 megawatts. So that's how an electronic tag looks like. So it has essentially a single path mentioned, and due to the interconnected nature of this, there will be multiple paths. So FTRs here stand for financial transmission rights. So in the market at the line 2 for this transaction, we will be allocating about 180 megawatts from west to east, whereas from south to north, we'll be allocating about 320 megawatts on this line, which is direct flow. Now this picture, this snapshot was taken after the power flow converged, and we can necessarily see there is some flow on the path 1-3, which has essentially no allocation as far as the market is concerned. But there is transmission, there is power flow on that line. So this is the most elementary example one could provide to exhibit what an unscheduled flow should look like. So I think I already said the contents of this slide, as in the power injected by the generation company at 3 will be divided as per the impedances on this line and the extended line via the bus 1. So that is one of the prime reasons, which is the interconnections. Now, for example, what is the side effect, or what is the disadvantage of having an unscheduled flow? For example, in this network, if there was a transmission congestion or a path limitation on this line right here, which is 1 to 2, and we have some unscheduled flow flowing over this line, which essentially superimposes itself, though it's not allocated, is going to cause congestions. And again, the owner of this line is, the rights for this line have not been allocated to the transaction. So first off, the transaction is using unassigned transmission rights, and again, it's also causing congestion. So these are primarily the side effects or disadvantages of unscheduled flows. Now, how to accommodate those unscheduled flows? So since the inconsistency is on technical level as well as the market level, either of those approaches could be used to accommodate these unscheduled flows. However, both the approaches need the modeling and the estimation of these unscheduled flows. As I'm going to harp on this a lot in this particular presentation, as in we use a linear estimator to estimate unscheduled flows. So this essentially is a technical level accommodation of unscheduled flows, and then later on those could be accommodated at the market level using cost functions. But the cost functions are not a context of this talk. So let's just ignore the numbers which I had put in on that particular network and assume that we have about a 40 megawatt unscheduled flow or a minor loop flow in that particular network in a clockwise direction. So we assume that there is like a looping flow here of power of about 40 megawatts. So this estimation is going to have a certain amount of confidence interval associated with it, and the only possibility of the estimation going wrong or we not having the exact amount of power flow is an outage in either of those electrical components. But again, we are not talking about outages, so it's the value of that minor loop flow is fixed or deterministic, if you will. Now, now let us discuss how an unscheduled flow will get a stochastic nature in it. Instead of the conventional generation over at the bus number 1, we had say 180 megawatt wind farm commitment at the bus number 1 to supply to the load at bus number 2. This certainly will lead to a stochastic nature to the power flow on the line 1 to 2, and the uncertainty will depend upon the commitment, like how much ahead of time was the commitment by the wind farm made, and the time window of the forecast availability, that is the forecast accuracy of the wind farm owner. Typically, wind farm outputs are better explained using probability density functions set up using the historical data of the wind farms. That's how typically the wind farm owners would want to forecast the dispatch. And again, there is one more topic which could be talked about here, which is the Markov chain processing necessarily by setting up different states of the wind farm output. And again, we're not going to talk about Markov chains either. The linear estimator. The linear estimator of the form hx is equal to z is being used by us right now to estimate the unscheduled flows. We don't have an intercept. That means we assume that the linear model passes through the origin. The H here is the incidence matrix, which are essentially our observations about the network. The dimension of this particular matrix should be number of branches times the number of regressors, and I'll show a sample H matrix in a little bit. X is the unscheduled flows which we want to estimate. Z is the difference branch flows, as in the difference between the market expectation and the actual flow. Actual flow is obtained after the power flow is converged. Setting up the our observation about the network is going to be translated via these loop selections. There are two techniques to select loops. One is visual synthesis and the other is algorithmic synthesis. Visual synthesis is useful only for little test networks which don't have complex connections. However, bulk interconnections, it's tedious and inaccurate to use visual synthesis since we don't have essentially that many visual aids available. Let us look at the nature of these parameters up here in the equation. The H matrix, which is our system observation, is necessarily going to be a fixed variable. That means it does not change unless there is an outage in the network, outage of transmission lines. X, which is being estimated here, depends upon the nature of the line flows, and Z is the essentially Z has branch flows. Branch flows will depend upon what the nature of generation resources we are trying to use. So here's the test system, which is slightly more complicated than the 3-bus network, and we have synthesized about 8 loops in this, which are enlisted in the left column. Like a loop is essentially a closed trail starting from one point and ending at the same point. For example, this is 2152. It's a loop, and the criteria to select loops was each transmission line should be used twice in opposite directions. Right now I'm still talking about visual synthesis, so it's little size networks and plain instincts, I would say. We have about 8 loops here, so we are trying to accommodate the unscheduled flows on all these 20 transmission lines using 8 regressors. And these are exhaustive loops. These are unique loops and should be able to provide all the information about unscheduled flows. And we will be using this observation to set up the H matrix or the system matrix of the linear estimator. So this is how it looks like. It has got a lot of elements, and let me just point out the dimensions of this. The number of rows will be equal to the number of branches. These are 20 rows, and these are about 8 columns, which is equal to the number of regressors or the number of loop flows we are trying to modify, trying to estimate. Now, the way the elements are allocated is zeros are simple. If there is no association between a loop and a branch, just put in a 0. The ones and minus ones are kind of tricky. That depends on what is the convention used to write these branches. If the branch in the loop is in the same direction as in this relation, as in if it's scanned as 1 to 2, then you put a +1. If it's 2 to 1, it's just a -1. There are multiple techniques we have developed actually to allocate these elements to the H matrix, as in GIS techniques and some graph theory techniques, but we won't discuss that in details right now. Now, setting up the simulation, we used 4 wind farms at different buses in the 14-bus network. The physical distances between these wind farms are justified by the line lengths, as in the spatial resolution of the network is used to locate those wind farms on the test network. The installed capacity is about 450 megawatts. Now we use the time series data, time series power output of these wind farms, essentially to run the Monte Carlo simulation. And to get the base case, we took in the mean values of these large time series of an annual scale, and then established a base case. The objective in this study is investigating the nature of unscheduled flows how it changes from a deterministic to a variable sense when we have large wind farms connected to the grid. And here the slack generation essentially accounts for all the transmission losses and the deficit of generation, if any, with the wind farms, or essentially the secondary market. With the expected values of the time series outputs of the wind farms and the fixed values of loads, we set up the base case, and these are the load flows. This is the converged load flow. As we can see, the table shows the megawatt flows on different lines. Now this is what the market expectation looks like. The market expects, we are trying to make market expectation as congruent to the actual power flow as possible. And then for about 500,000 different values of the wind farm outputs, we try to run the Monte Carlo simulation. Enlisted at the second bullet are the installed capacities of different wind farms. On an average, if we see 17% of the load is being supplied by the wind farms, which is pretty huge. And again, as I mentioned, the location of wind farms was based on spatial regulation. The wind farm voltages are already regulated. We received this information directly from the data providers. So now, where is the source of variability? That's the question. The right-hand side of the linear estimator, which was the z vector, it has the market expectation minus the actual flow. That is the difference flow on transmission lines, difference power flow on transmission lines. So the market expectation is going to be fixed, as I showed in the previous tables. The actual flow will be varying depending on the variability of the wind farm. So we have H, which is fixed, X is to be estimated, and the Z on the right hand side is the variable where the transmission line flows are being accounted. Now, how do we solve this problem? The most common approach used to solve such a problem is ordinary least squares. The expression is given as x hat OLS is equal to H dash H whole inverse times H transpose times Z. So that is the estimated value of the loop flows for the given system, for the 14-bus system. It is very important to understand or interpret the statistical confidence of the estimates of the unscheduled of the loop flows so obtained. When we did the statistical testing on the system observations, that is the H matrix, we found out that it has got severe multicollinearity issues. We will be discussing how to deal with multicollinearity issues, but I'll be providing some results first. So for the scenario A, essentially we had only wind farm outputs changing and keeping everything else, that is the load value and the generation and the conventional generation values fixed. These are kind of interesting plots. As we can see, the probability is being concentrated at specific points in the graph, as in we have a sort of an impulse here, here, and so on and so forth. So the point here is that impulse necessarily represents the maximum power output of the combined 4 wind farms we have. Then what is the most probable output of all the 4 wind farms together? That's where the most probability occurs. In the scenario B, we tried to understand what if even the load changes on an annual basis. So all these simulations were on an annual basis with the annual time series of the wind farm outputs and annual load patterns. So essentially the load patterns were normal in distribution, and we wanted to see how does this interaction work. So we found out that these plots are also normal, with essentially the probabilities of the peak probabilities were obtained at points where the wind farm output and the load variability was highest. Now what can we infer from these points? I already explained what the plots look like and what they mean to us, but since these ordinary least square estimates are supposed to have minimum possible variance, but the observational matrix has multicollinearity, so this certainly is not the minimum possible variance. So we have to counter this Ordinary least squares have, since I already mentioned, they are unbiased. We need to bias this estimation technique using a biasing factor. The biasing factor is added along with along with a unit matrix in order to obtain better estimates of the unscheduled flows. This technique is called as the ridge regression, and we are also investigating one more technique as the robust regression. There are again two techniques of selecting the biasing factor in this estimation technique, which is the graphical and the analytical technique. The expression for the analytical technique is given in the second part of the equation, and it essentially uses the estimates already obtained from the ordinary least squares. It's a proven fact that even if after biasing this unbiased linear estimator, only 50% of the regressors might shrink, as in the estimates will improve. However, the computation time has increased since we have to calculate the value of the biasing factor each time. Now, looking at these plots, we can observe that for the first plot right here, the estimated variance increased, and for the second plot, the estimated variance decreases since the histogram shrinks essentially. So this is as per. So the top plot represents ordinary least square estimates, and the bottom plots represent the ridge regression by analytical means. Here is a picture which is kind of looks really crowded, but these are the plots of 8 regressors which we wanted to estimate in the given test diagram, and it's the top block. The numerical value represents the variance of the histogram or the distribution. It is about 5 of those regressors have shrunk, so at least 50% of improvement in the estimation technique was observed here. The rest of the 3 regressors have not actually showed a lot of improvement in the estimation. So what do we need? How do we take the next step? Because the target here is to develop this framework on test networks and take it to applying towards larger systems like bulk interconnections. So we want first of all a synthesizer or a loop detector which will automatically detect loops in a network for a large graph essentially, because bulk interconnections typically have about 15 to 20,000 buses in about 20 to 30,000 branches. I'm talking about standard bulk interconnections in the United States. So we have to necessarily adopt the algorithmic synthesis of loops here. And again, the choice is still governed by the system size. We named this algorithm we're trying to develop at Colorado State is the loop detection algorithm. And the algorithm will detect, for any given graph, it is supposed to detect closed loops in that particular graph. And since we are applying essentially graph equivalents of power system networks, we stick to the terms of. I'll try and use. I'll use the terms of graphs and power system networks interchangeably. So we use essentially here graph theory and some combinatorial techniques for synthesizing loops, and special attention towards the order of complexity and storage requirements has been catered. Now, I will not be discussing the details of the loop detection algorithm here, since we have a publication in process right now for the same. So I'll just give a hint of what this loop detection algorithm should do. It's essentially a 2-step algorithm, and it's derived from Dijkstra's theorem or Dijkstra's minimum path algorithm, and the A-star heuristic search algorithm. The order of complexity of this algorithm is V squared. V is the number of vertices or nodes in the network. And we have coded this, we have already proved the algorithm, derived the order of complexities for storage as well as execution times, and trying to test these particular algorithm on larger networks. So the results here, they don't look really clear in the in the table, but this is a 30-bus IEEE test system which has been which we use the loop detection algorithm to test it, since we still can synthesize loops in a 30 bus network and try to verify the results. There is an interesting phenomena that occurs when you solve algorithms uh, like these on test systems, since we still have visual aid. When we start solving an algorithm, a network like this, we typically it is sort of analogous to eating a donut. If the donut has a steel ring in the inside, you just start eating the donut from periphery. In the end, you're going to be left with the steel link inside. That's what essentially the last loop of this algorithm is. That was something which was really fascinating for us, and I'm going to just highlight that particular loop here. Uh, so the loop we detected in the end was right here: 10, 22, 24, 23, 25, 18, 19, 20, and back to 10. So this is sort of the innermost link graphically for this particular power system network. So in short, we started solving this network right from the periphery, and then it kind of reduces the network one by one as we obtain information from it, and simply we obtain at the end all the loops in the test system, and those can be used in our framework again for detecting for estimating unscheduled flows. Some concluding remarks. An attempt for establishing what is the impact of wind energy penetration on the nature of existing unscheduled flows. So unscheduled flows do exist irrespective of conventional or non-conventional generation. That impact has to be documented well, and a framework to estimate those is attempted here. We use a linear estimator to model the unscheduled flows. Advanced estimation techniques are also suggested. The nature of unscheduled flows is largely the change in nature, which is the stochastic nature, is largely influenced by how variable the wind farm output is going to look like. Then we are also developing an automated framework to establish this loop flow framework. Since all the techniques essentially will be automated, loop synthesis will be automatic, biasing factor selection will also be automatic, and so a complete automated framework is being developed at our lab right now. And these are some of, we acknowledge WECC for funding this project via DOE's fund. I would acknowledge Dr. Sid, who is my advisor, and Professor Dan Zimmerli, who's helped us set up the graph theory algorithms. And these are the few publications which are submitted, under construction, so on and so forth. And that's pretty much it. I don't know where to find the chat.
I have one question.
Yes.
Did you have the chance to get the real data and look, let's say, as part of the network that actually the loop flows in the, let's say, part of region or one state?
So the question was, did we get to execute and verify the loop flows on a practical network on a state level? So the target here is to extend this study on the Western interconnection, and typically they don't do statewise essentially power system operation. They do it on an area wise or a region wise. Secondly, we will be doing this. The way we are going to verify our results is analyze the congested paths. Analyze the congested paths in the Western interconnection after we apply our framework, because there are historically a few paths on the Western interconnection which are congested because of unscheduled flows, especially the lines which run from the northwest to the southwest. So those are termed as qualified paths, and we will be analyzing those since they will be detected by the loop detection algorithm. But no, right now, no.
A very simple question. Are you using a virtual wind farm, or are you working with?
The 4 wind farms we used are practical wind farms somewhere in the northwest, and the readings we used were actual power injections at the point of interconnection. So there's no simulated wind farm. There's an actual wind farm.
We're in a classroom. Yes.
I have another question.
Sure.
So, did you investigate at what type of penetration might be causing stability in the loop flows?
Instability.
Sorry, like as a function of the penetration of wind farms,
right?
Or injection from wind farms,
right?
You said that 17% is already quite a lot. And,
yeah.
Yesterday we looked at in Denmark, portions of their grid are running at 50% already.
Right.
Now, pushing at their own network. So in this test model, I guess this is all the IEEE 30 buses. Right?
Yeah.
What is the portion of wind farm, or like as you increase generation,
right,
from stochastic sources?
Right.
At what point do you see a greater distribution?
Right. So the question was, is there a penetration level essentially to kind of bookmark which will cause congestions in transmission lines? So since we are right now dealing with test systems, we place the wind farms using just the physical distances of the buses. So we just place, okay, let's try this. The distance between two wind farms is about 100 miles. Which line we should be able to justify the spatial resolution. So essentially there are thousands of combinations where you could place those generators and then run your system analysis and then see, okay, you know what, this line got congested, that line got congested. So essentially the takeaway from the study is going to be, when we apply it to an actual system and which has already upcoming or existing wind farms, that should help us provide a system specific number of wind penetration that will cause congestions. But right now, I mean, I could say, you know, branch 10 to 11 is getting congested, but that doesn't mean anything because there is no actual wind farm there. We have superimposed the wind farm onto the network using just the special resolutions.
Do you test for network violation?
Yes, we will be, because right now we are developing the statistical confidence intervals, and that should be, the statistical confidence intervals should help us compare with the line flow limitation, line flows, or the available transmission capabilities of the lines, and then we will be able to conclusively say, you know what, with this confidence interval we can say that line X to Y will be congested if the wind farm penetration at so and so bus is 200 megawatts.
For a given number of hours.
Exactly. Yeah. It should be.
Any more questions? Well, let's thank one more time Manish for his presentation. We'll have the next seminar on October 19th with Branko Kosovic from NCAR. Stay tuned to it, and hopefully we'll see you there. Thank you.